Good morning to all of you. In the last class, we have started with module 2. Specifically, we have introduced MOSFET amplifier configurations. We have seen three different types of MOSFET configurations, namely common source configuration, common gate configuration, and common drain configurations. Following various types of configurations, we have discussed characterizing the amplifier. Various parameters that are required to characterize amplifiers has been discussed in the last class. Then we have discussed common source amplifier without any biasing elements. In today's class, we are going to discuss again common source amplifier with all the biasing elements. Now, in common source amplifier, basically a single stage, as we can see, this is a discrete version of common source amplifier. This amplifier has been built by using various elements, resistance, capacitances, current sources, etc. So this is a discrete version of a common source amplifier. In this discrete version, we can see that we are applying a signal that needs amplification at the input for the transistor, and the resistance of this signal source V signal is labeled as R signal. This is nothing but signal resistance, which is an internal resistance of the AC source or signal that needs amplification. And the signal is V signal is fed to the transistor via the capacitor called as coupling capacitor here. We know that the important property of a capacitor passes AC signals and it blocks DC signals. So therefore here we are applying AC signal to be amplified through the capacitor. So AC signals are passed efficiently or easily through this capacitor. And there is a resistance here which is Rg. Usually this Rg is going to be a large value. Now the signal which is applied to the gate and the source, this is an input for the common source amplifier that gets amplified in this using this transistor, which is a fundamental element in amplifier is transistor. So transistor does here amplifying action, and we can see the amplified signal appears here at the drain of the MOSFET. So the AC and DC signal appears here, but to filter out here, the DC will be blocked here through the usage of a capacitor called as a CC2. CC2 is another coupling capacitor. This capacitor used here blocks a DC going out from the drain here. Only AC signal is allowed to pass through the coupling capacitor CC2, and the AC signal will drop across the load resistance RL. RL is usually a loudspeaker. The loudspeaker is modeled as a load resistance here, and we are going to measure output voltage across this load resistance RL. Now in this circuit, what we can see, what it differentiates with the circuit that we have discussed in the last class is the biasing part here. So if you can segregate this circuit into the AC and DC equivalent, we can see the biasing part in the DC equivalent. So prior to the moving into the different AC and DC equivalent circuit, let us see other points here. Why the name common source amplifier? The reason why it is called common source amplifier is because for AC signal, this point becomes ground, because capacitor will be a short circuit. This capacitor is called bypass capacitor, and this capacitor will be short circuit for AC signal, and now source will be at ground terminal. Since source is at the ground terminal, because CS will act like a short circuit for AC signal, now the input is applied between the gate and source. So there is a AC signal here which is V signal that is applied between the gate and source here. So this is our input signal that we apply here. And output is measured between the drain and source here. So we are going to measure output signal between drain and source. So therefore, since the source serves as a common point between input and output, therefore the name is common source amplifier. Now to obtain the DC equivalent circuit, we are supposed to open circuit all capacitors here. The capacitors, what we have seen here, if we remove these capacitors, here, the capacitor here, since capacitor acts like it blocks a DC signal and passes the AC signal. So therefore, we can block, we can remove the capacitor from this circuit. Wherever capacitor is there, we can just ignore it or open it. So therefore, that equivalent circuit which is produced by removing capacitor is called as DC equivalent circuit. So the resultant DC equivalent circuit is as shown here. After removing these capacitors, the resultant equivalent circuit contains the RG. There is a current source here, and there is a supply here, negative supply minus VSS, and there is a positive supply which is VDD, followed with there is a resistance RD. So therefore, the DC equivalent circuit looks like this. So now we will see here, we will just analyze the DC equivalent circuit. What are the DC levels required to establish so that the MOSFET performs an amplifying action. So we'll see that step by step. So in this circuit, the differentiating factor is we are using here a bias circuit called as constant current source biasing. Though this biasing is not there in our syllabus, I suggest you to watch my earlier videos to understand more about constant current source biasing. So here, constant current source biasing is nothing but a current mirror circuit. We will see why this circuit is called as current mirror circuit here. The circuit which is employed here is nothing but the constant current source or current mirror circuit. If we expand this circuit, so we can see the current mirror circuit is made up of two transistors, namely Q1 and Q2 here. The reason for using constant current source biasing here is, so the current required to flow in this branch is controlled by this current source. So therefore, this current source can be adjusted according to the required value. One of the important aspects of biasing is maintaining the constant current through the drain and source. So this we have seen in various other types of biasing. So the current flowing here, the drain current here, which varies with reference to the various parameters here. But if I use a biasing scheme called as constant current source biasing, the variation in this the current which is drain current here in this case, that will be minimal. Now let us see the details of this constant current source, which is nothing but a current mirror circuit. So the current mirror circuit comprises two transistors, which is Q1 and Q2. And here the assumption is we assume that these two transistors operates in saturation region. If let's take first for the Q1 transistor. If Q1 transistor is in saturation, therefore the current flowing through this must be a saturation current, and the mathematical expression for this is given by the equation 1. So the I reference current is nothing but the saturation current of the MOSFET, which is equivalent to 1 by 2 mu n times COX into W by L. W is nothing but width of the transistor and L is nothing but length of the transistor. So these are the parameters of the transistor MOSFET, and W by L is called as width and length of the MOSFET. So here the current I reference depends on gate source voltage. The gate source voltage applied here, it depends on the gate source voltage, and also the I reference depends on the threshold voltage Vt. So therefore the saturation current equation is 1 by 2 mu n COX times W by L into VGS minus Vt whole square. So now if I apply KVL in this path, we get a equation which is given here. So which is minus VDD times I reference times R plus VGS minus VSS. So so if we simplify that, that gives me equation 2. So equation 2 is VDD equals I reference into R, let's say drop across this resistance, plus VGS, which is gate source voltage, minus this negative supply here. Now why we need equation 2? So if you can observe equation number 1 and 2, so this reference current I reference, it mainly depends on gate source voltage. And again you can see here also we have two variables, which is VGS and I reference here. We can, from this equation number 1 and 2, we can solve for I reference here. And also the I reference current can be controlled through this resistance R. Varying this R, can can lead to the change in the reference current, I reference here. Okay, so these are the two equations which will help us in determining the reference current here. Now, this current mirror circuit, as we have mentioned already, it contains two transistors. If we do certain assumption, we'll discuss what assumptions to be made here. So the current flowing here, this ID current, drain current flowing in the Q2 transistor, will be the mirror of this reference current here. So such circuits are called as a current mirror circuit. That means current flowing in the one branch, we are going to produce same mirror current in the other branch. So this type of this type of circuit is called as current mirror circuit here. As I've already said, this I reference can be varied by varying the resistance here, and if we do certain assumptions here, then current produced here will be exact replica of this reference current here. We will see that what assumptions to be made here in order to make drain current flowing in through the Q2 same as the reference current here. So the assumption is we need to take matching transistors, Q1 and Q2. Matched transistor meaning is, so these two Q1 and Q2 transistors must be identical. Identical in the sense the process parameters of this, namely mu n COX and width by length of this transistor should be exactly equivalent to the Q2 transistor. So in other words, if I say that if these two transistors are matched, in such case, ID will be equivalent to I reference here. The current flowing in this branch will be exactly equivalent to the current flowing here. And if you look at the circuit in amplifier, DC equivalent circuit here, the current that is flowing here is nothing but the current through the current source here. This current source, so far we have discussed, is the internal circuit of this current source. So this is nothing but ID. ID will be equivalent to I. That means if I am able to control this I reference by varying the resistance here, that means I'm able to control this I, which is nothing but the ID. Okay. Now ID will be equivalent to the I reference, which is also equivalent to the I, which is the current flowing through the a constant current flowing through the drain source branch here. Now we know that transconductance GM, this equation we have derived in module 1. So the transconductance GM, which is equivalent to square root of 2 times mu n COX times W by L times ID. This drain current here or reference current here now depends on the transconductance depends on this drain current here. That means the drain current what we set here that decides the transconductance of the amplifier here. So transconductance is like a beta in case of a bipolar junction transistor. The amount of amplification is decided by the transconductance here. So this transconductance in turn depends on the drain current, DC drain current of the transistor. Okay, the amount of current that is flowing here, that decides the transconductance here. Now, if you apply KVL here, so we can get the output equation, output voltage equation V naught. So V naught equals VDD minus ID into RD. So this V naught equals the supply voltage minus drop across this. So the current flowing through this is ID here. So this drop across this ID into RD, that gives me the VDD minus ID into RD, that gives me the output voltage. So that means the current flowing here will decide the output voltage, okay, which is calculated using this equation here. So this is the saturation current, the current that flows here, since we assume that MOSFET operates in saturation region. So therefore, the saturation, this current flowing through this transistor can be modeled through the saturation current now. Let us go this step by step. Earlier I told you about this transistor, the matched condition of transistor now. Now let us see that what will happen when we assume these two transistors are identical. So this is once again the current mirror circuit. So the same equations which we already discussed, once again it is rewritten here for your reference. So current flowing through this I reference is a saturation current which is given here. The current flowing here in the second branch is again a saturation current given by this. We can make an observation here, since this transistor we called as Q1. So the current flowing here is W mu n into COX, half of mu n into COX into W by L. We have indicated here index as 1. That means the current flowing here is W by L of sub 1 into VGS minus VT whole square. Whereas current flowing here, we have taken a different width by length ratio. This is W by L sub 2. This is the current flowing here. So if you take a ratio of this I by I reference, so which is given here, which you can divide equation 2, this can be called as equation 2 and this is equation 1. If we divide equation 2 by equation 1, that is I by I reference. So all these terms will get cancelled here, mu and COX here, VGS minus VT, VGS minus VT whole square. I assume that the VGS of applied here is also same as VGS of this because both transistors share the gate here. So therefore, VGS here will be same as VGS here. So VGS, and also I assume that the threshold voltages of these two transistors are equal. So therefore, the only parameter, only variable between these two equations will be W by L. So even if you make a W by L of this transistor same as the W by L of this transistor, then I becomes equal to I reference. This is called as a current mirroring. Current mirroring means you are producing a current in other branch which is same as the current flowing in this branch here. Okay, so the current here mirrors here. So this circuit is called as a current mirror circuit. So the biasing scheme using current source or current mirroring circuit is most popular than the other kind of biasing schemes here. Okay. Now, if you look at a common source amplifier, so the AC equivalent circuit can be obtained. So far, we have discussed DC equivalent circuit and we have discussed constant current source, which is mainly main circuit required in the biasing scheme. Now we will discuss the AC equivalent circuit. So once again, if you reconstruct, recollect the same common source amplifier that we have discussed, so from this circuit we can obtain the AC equivalent circuit. We know that for AC, capacitor act like a short circuit. So all this capacitor will behave like a short circuit for AC signal. So this will help us, the AC equivalent circuit will help us in understanding in which all the branches this AC signal flows here. So AC signal directly it flows to the ground via this source here, and AC signal gets applied to the gate of a transistor, and AC signal will get dropped across the load resistance here. So DC must not be there, DC must be grounded for the AC equivalent circuit. So this DC voltage sources will get eliminated for the AC equivalent circuit. So we see that RD straight away goes to ground here for the AC equivalent circuit, and here the capacitor becomes the goes to the ground directly. So the source is tied to the ground here. So source is directly grounded here. So this circuit is the AC equivalent circuit of common source amplifier. Now we have seen both the versions now, DC equivalent circuit as well as AC equivalent circuit. The one and only circuit which has got both DC equivalent and AC equivalent circuits are amplifier circuits. Okay. Now, before we move on to the deriving, the equations of common source amplifier, now let us take an example here. So once again, we are showing here the common source amplifier, which has got VS signal source, R signal internal resistance, capacitance CC1 coupling capacitor. We have CC2 here. There is a bypass capacitor. There is a current source here, which is a current mirror circuit here. So now we have done here step-by-step analysis. So the current source here is expanded here. You can see here the current source here. So this is minus VSS, which is shown here, and this current straight away goes to the DC equivalent circuit here. So DC equivalent circuit comprises RD, VDD, and RG. So you can see here this is the DC equivalent circuit here. The whole circuit, this whole circuit represents expanded version of a DC equivalent circuit. Okay, including the current mirror circuit here. Okay, so earlier we have shown that this here we have shown with a current source that's straight away going to the minus VSS. Now we have expanded this current source with a current mirror circuit here. Okay, now let's assume the few values here and try to calculate voltages and currents at each branch here. So let's assume that this half into mu n into COX times W by L, 1 for the Q1 transistor is equal to 1, and this is multiplied with VGS minus VT whole square, because we assume that this transistor is going to operate in the saturation region, So the another equation, if you apply KVL here, so which gives me I reference is equal to VDD minus VGS plus VSS. So solving for I reference, which gives me as 1 milliampere, and we can also solve for, since there are two equations and two variables. One variable is I reference, another variable is going to be the VGS. So that gives me the value of VGS as 2 volts, assuming other values as a resistance value as 18 kilo. So now we came to know that, so the VGS value is going to be 2 volts here from this point to this. VSS is taken as minus 10 volts here, minus VSS, and we assume that both transistors are going to be in saturation. There will be a common VGS for the both Q1 and Q2. So VGS is now, it's 2 volts here now. So now with that, with having known this, know the VGS, we can calculate voltage here. So voltage here can be calculated just by subtracting this minus 10 volts from this 2. So we get minus 8 volts here. So once we know the voltage here, that this is shown further calculations. We'll see that how to calculate that. So for Q2 transistor, the current flowing here is going to be 1 milliampere, because the I reference is going to be 1 milliampere. So this circuit, if I assume both transistors identical, so therefore same 1 milliampere current also has to flow here. So I is equal to I reference, which is equal to 1 milliampere. And if I assume both the width and length of this transistor is same as width and length of this transistor, the current flowing in this branch will be 1 milliampere. So if 1 milliampere current flows here, there must that means there must be a VGS of 2 volts exist here. So that's voltage exist here. Okay. Now let's move on to the Q3 transistor. So for Q3 transistor, also same, since I assume that this transistor also operates in saturation region. So if 1 milliampere current flows, so same 1 milliampere also should flow here. So let us see now other voltages of this. Uh, so I said there must be a I is equal, since I is saturation current flows through the Q3, so same current equation applies here. So we know that I is equal to 1 milliampere, and also we know that to produce 1 milliampere current here, we require VGS of 2 volts here. Same is applicable even for Q3 transistor. The meaning is to produce 1 milliampere current here, this transistor gate source voltage must be equivalent to 2 volts here. So the gate source voltage, if it is equivalent to 2 volts, we know that this gate terminal is grounded here. There is a 0 volt exist here. We know that the VGS is equal to VG minus VS. VGS is known. VG also it is known. From that we can calculate what is VS. So VS, from this we can estimate it is going to be the minus 2 volts. So VS is going to be minus 2 volts here. Okay. Now, so we came to know that VS is equal to minus 2 volts. Now let us try to estimate what is VDS. So VDS is nothing but, see here we have minus 2 here, and we have minus 10 exist here. So therefore minus 2 minus of minus 10 gives me the 8 volts here. So from this two voltages, we can estimate what is drain source voltage here. So drain source voltage is going to be 8 volts here. And so we can also estimate drain source voltage here. So drain source voltage here can be estimated, as we know already, gate voltage equals minus 8 volts. So this voltage here, so same voltage must exist here, so which is minus 8 volts here. So minus 8 volts exist here and minus 10 volt exist here. So therefore the difference of this gives me the voltage across the VDS across this Q1 transistor, which is equivalent to the 2 volts here. Okay. So this is going to be the current mirror circuit. Now let us go a little bit above and see the swing of this circuit here. So since we know that this voltage is minus 2 volts, now we can calculate what is the voltage from this to ground. So if you apply thumb rule here, supply from here to here, there exists a 20 volts. 10 minus of minus 10 gives us 20 volts. So already we know that 8 volt is dropping across this, and so remaining is going to be the 12 volts. So 12 volts means if this voltage can be estimated here, this voltage is now which is equal to 4 volts here. So 4, this point we know the voltage here is -2, and from this you can see that the difference can be calculated VDS across this. So but for us what is important is the drain voltage here. So from here to here there is going to be the 20 volts. From that we can calculate what is the voltage at the drain point here. So drain point voltage is nothing but the supply voltage minus the drop across this. So drop across this is nothing but which is 6 volts here, because of a 6 kilo ohm resistance is there, and 1 milliampere current is there. So the product of this two gives me 6 volts here. So from this we can estimate what is the voltage here. So we can use VD equals VDD minus ID times RD. That gives me VD as 4 volts. Now, this is very important for us to calculate the swing. Suppose in case if I apply AC signal here, to what extent the positive signal goes, and to what level the negative signal goes. That can be easily, the swing can be estimated here. We know that positive swing can go up to VDD, which is 10 volts, and the negative signal can go up to VG minus VT, VGS minus VT, VG minus VT actually. So VG minus VT is nothing but which is 0, minus VT is minus 1 volts. So negative signal can go all the way up to minus 1 volt. So now we can see the difference here. 10 minus, so here we already have the drain voltage at 4 volts. The 4 volt exists here at this level. So across 4 volts my AC signal will swing. Now positive signal, since 4 volt already exists here, the maximum signal at positive peak can go up to 10 volt here. Therefore 10 minus 4 gives me the difference as 6 volts. So the positive excursion of AC signal can go up to 10 volt. The signal can the swing is going to be 6 volts here. Above 4 volts the signal can be it can swing up to 6 volts, and below here since it is minus 1 volt here, 4 minus of minus 1 becomes 5 volts here. Below negative peak can swing up to 5 volts here. As we can observe here, the swing is not identical. That means the output signal which we are getting here, the amplified version, the swings are not identical. That's one of the limitation which we can say here. But if you compare with other biasing schemes, the swing is going to be very large here. Okay, in the previous three biasing schemes that we have discussed, so the swing is going to be very less. But here in this kind of biasing, in this means it is a biasing using a constant current source. So this has got a larger swing compared to other biasing schemes. Okay. Now let us see some drawback of this current mirror circuit. So we have said that so if you make these two transistors identical, the current flowing here in this branch is a mirror of the current flowing here. But let us see the drawback of this. So if we plot drain versus drain source VDS versus ID characteristics, the curves will be almost a straight line here. This circuit works very well. I mean, the current flowing in this branch will be mirror of this current, provided if these two transistors are identical. So if these two transistors are identical, and moreover they are ideal, so then the current flowing here will be same as current flowing here. So this is going to be the ideal characteristics of both the MOSFETs here, a straight line. So that means resistance between the drain and source is going to be infinity for this both the transistors. If that is the case, these two transistors will exhibit a straight line characteristics, provided if these two transistors are ideal. But practically, for practical transistors, I mean the transistors are no more ideal. If that is the case, so then there will be a slope, the VDS versus IDS characteristics for each one of these transistors exhibits some slope in the characteristics. That means they have a finite amount of resistance across this. Now let us see that what are the problems it creates when we have finite amount of resistance here when we choose practical transistors here. As we can see here, there is a 2 volts exist here because of some resistance between the drain and source. and there exist the 8 volts because of a resistance between the drain and source. So this difference in voltage, drain source voltage, creates a different current in I and as well as I reference. So let us see here. See, for 2 volts drain source voltage here, we may have some current here, and for 8 volts drain source voltage here, we may have some different current here. So you can see here the current levels are totally different now. So now this difference shows that I is not equal to I reference. I is greater than I reference here. Okay, so this is the problem of current mirror circuit. However, if you make two transistors ideal and more identical, then in such case the curve will be a straight line, the resistance will be infinity, and both voltages will remain same here. Otherwise, there will be a difference in resistance, and the current flowing here will not be the mirror image of this. Is the main requirement of current mirror circuit here. Okay, so already we have seen the AC equivalent circuit of a common source amplifier, which is once again shown here, AC equivalent circuit. For the AC equivalent circuit, now let us go further in detail and analyze the AC equivalent circuit of common source amplifier. Now here, to go further, we are going to replace this MOSFET with a T model. Okay, so you can see here the MOSFET replaced with its T model. So T model we have discussed in module 1. The students can refer to my videos uploaded in my channel to understand the T model. So however, here T model is used in analyzing this common source amplifier, AC equivalent circuit of common source amplifier. So we have an AC signal that is applied here. This is an internal resistance of this AC source. We have an RG here, but only difference is the transistor here is replaced with its T model here. The T model comprises a current source and a resistance which resembles in the form of a T. This looks like a T shape here. So we have a T appearance here. Okay. So this is called as a T model. T model is accurate model that models the behavior of MOSFET. That helps us in understanding the circuit here. Many times we do analysis, assuming the MOSFET is ideal, but here to obtain practical, the mathematical, derivations, we need to replace with its model. So one such a popular model and widely used model is T model here. So this current source here the resistance here 1 by Gm is the resistance value, and the current flowing here is going to be Gm times Vi. This is a dependent current source. So the current flowing here depends on transconductance here, which is Gm times Vi. Vi is nothing but applied here between the gate and source here. This is Vi. Okay, so this depends on the current flowing here depends on transconductance of the MOSFET, and it depends on Vi. Okay, in other way, you can say that it depends on resistance and it depends on the voltage applied here. And also the T model has got the resistance here, which is R naught here. R naught is the internal resistance that exists between the drain and the source. So this ground point is the source here. So small R naught indicates it is an internal resistance of MOSFET. And at this drain point, we can see the external elements that we have used here. RD is shown once again here, and RL is again here. So this is output is measured across the RL here. Now using this circuit, we can derive the expressions for input resistance, output resistance, voltage gain, overall voltage gain. So all the equations can be derived very easily with the help of this AC equivalent circuit using T model. Okay. Now let us proceed further now. Using this same, the AC equivalent circuit using T model, same circuit is written here for your reference. So now we can obtain the output voltage equation here. So V naught equals now, which is the current flowing here. V naught is nothing but drop across this resistance. Now all these three resistances, now what we have seen here, RD, R naught, are they in parallel. So therefore we can replace that with a single resistance here. Now we can calculate output voltage across this resistance here. So output voltage equals now minus I times the resistance value. So minus I is nothing but which is Gm times Vi. So minus Gm times Vi times the resistance, total resistance value, R not parallel with capital R sub D, parallel with capital R load resistance here. Okay. So now we can replace this Vi, which is an input signal here, with the expression given here. And this expression can be obtained by applying voltage division rule across this. So Vi equals now V signal into Rg divided by R signal plus Rg. So this Vi equals now this V signal times the resistance value divided by Rg plus R signal here. Rg plus R signal. This is actually the Vi across this Rg. So once we substitute here for Vi, so we can derive the expression for AVS. So AVS is nothing but it is V naught by V signal. So if you substitute here, this now whole equation will be in terms of V naught and V signal. So V naught by V signal becomes now minus Rg divided by R signal plus Rg into Gm into R naught parallel with Rd parallel with R. This is also called as overall or total voltage again here. Since Rg is going to be very large compared to the R signal, so Rg is going to be very large if I do this assumption in this equation. So R signal becomes negligible. If R signal becomes negligible, Rg cancels here. So therefore AVS becomes equal to minus Gm times R naught parallel with Rd parallel with R. This is the expression for overall voltage gain. Now let us derive the input, find the input expression for the input resistance. So input resistance seen from between the gate and the source. This circuit has got just an input resistance as Rg. So therefore straight away without deriving we can write Rn is equal to Rg, which is very large of course. Okay. Now, to estimate the output resistance, as we have said in the topic while discussing the topic of characterization of amplifier, we need to connect an external temporary voltage source, which is namely Vx at the output, and the current that is resulting by from this voltage source is Ix. So now here we have an AC equivalent circuit. To estimate R out, we need to connect a resistance here. So definition of R out is equal to this voltage source that we are connecting here Vx divided by Ix. Here input voltage should be 0. That means we should not apply this signal source. If you make this signal source 0, this part will get eliminate here. You can see this part is eliminated here straight away. It goes to ground here. So we have ground here, and the current flowing through this current magnitude also we have seen it is Gm times Vi. Since V signal is 0, Vi also will become 0. So therefore current flowing through this will be 0. The remaining circuit which appears to be like this, which has got R naught and there is a temporary voltage source Vx, and there is a current flowing because of this Vx. So this is the definition of R out. R out is equal to Vx divided by Ix. So now if we, this is the definition now, R out is equal to Vx divided by Ix here. So provided if the signal source should be 0 here. So with this, you can easily estimate the output resistance. Of course, if you look at from this output side, from there, the output resistance is now equivalent to R naught itself here. In case if you have RD here, then in such case it becomes the output resistance becomes small R naught parallel with capital RD. Okay, so this is the output resistance of common source amplifier. Now, so far we have discussed output resistance without connecting any resistance at the source terminal was straight away it was grounded now, grounded so far. But now we have another circuit which will see the working principle of this circuit. The title of this circuit is common source amplifier with Rs. So previously what we have seen is common source amplifier without Rs. That means RS is a short circuit. There was no RS, and the source terminal was connected to the constant current source, and the tender was connected to the supply. But now we have added intermediate resistance here, Rs. So we will see that adding this resistance in what way the performance of the circuit gets improved. Okay. Rest on the elements of circuit remain same. The only addition is we're attaching the resistance here, Rs. Okay. So in an overview, we can say that by connecting a resistance Rs, the circuit increases the stability, DC bias stability. The meaning of this is that the meaning of increases in DC bias stability is the current flowing here that will be more stable compared to other biasing schemes when we use RSCO. But other side we have a drawback also by connecting RSCO. There will be a drop in the voltage gain. So the voltage gain of a common source amplifier will be larger than the common source amplifier with RS. Okay, that's one drawback what we can see. That means we're going to get a benefit here and we're going to have a loss here where the gain decreases here. So here again there is a trade-off between choosing the circuits between a common source with RS and without RS. Okay. Now let us go through the separation of AC and DC equivalent circuit here. So again, to make this whole circuit, to extract DC equivalent of this, you have to remove capacitors here, removing this capacitor here, here, and here. That becomes a DC equivalent circuit, which is shown here. This is the DC equivalent circuit. To draw the AC equivalent circuit wherever there is a capacitor, we need to short circuit them. So short circuiting capacitance here and now. So the capacitor becomes a short circuit for AC. Since the capacitor passes AC signal, the resulting circuit is shown here. So this is the AC equivalent circuit, and this is going to be the DC equivalent circuit here. So now we will see we'll derive an expressions for AC equivalent by considering the AC equivalent circuit. So here one assumption what we need to do is while replacing the transistor here with transistor with T model, we need to ignore the resistance R naught. That means we need to consider R naught as infinite value. So this is because to simplify our analysis. Now let us see the rewrite the AC equivalent circuit. The AC equivalent circuit is as shown here, which contains all the elements that we have discussed earlier, except there is no R naught here. So R naught is neglected because including R naught will complicates our analysis here. So R naught is nothing but it's a resistance connected between drain and the source. It is an input internal resistance of the MOSFET, which is connected between the output and the input here, which connects across between drain and source here. That's ignored in this circuit here. So now we'll try to analyze this circuit here. So this is a signal that needs to be amplified, is applied via the R signal, that is nothing but internal resistance here, and we replaced MOSFET with its T model, which contains current source here and then resistance 1 by GM. Only thing is R naught is not there here. Now, so current flowing here, I can be derived here using mathematical equation here. This current flowing here, I here, and the same current flows also here. This current here, this can be derived by using the voltage here. The voltage that exists between this point is Vi divided by total resistance is now 1 by Gm plus Rs. So 1 by Gm plus Rs here. That is the amount of current that is flowing here. That is the expression for I. So I is equal to Vi divided by 1 by Gm plus Rs. On simplification, this equation becomes Gm goes to numerator. Therefore, I equals Gm times Vi divided by 1 plus Gm into Rs. Here itself we can observe the drawback of common source amplifier with inclusion of Rs. The current here, expression, if you observe current expression here, we have a denominator factorial 1 plus Gm into Rs. This shows that the current is reduced by a factor of 1 plus Gm into Rs. We have also seen the I expression without Rs. Without Rs, the expression for I was Gm times Vi. There it was, we don't have this expression here, but the moment you add this resistance Rs, we will have a denominator term 1 plus Gm into Rs. Now, this is going to be the current expression here. Now, VGS, voltage between this and this can be estimated, easily, by applying voltage division rule. So VGS equals this you can VGS, this gate to source here, and here we can apply voltage division rule. VGS equals, across this voltage existing is VI times 1 by Gm plus divided by 1 by Gm plus Rs. This is a voltage division rule which we can apply across this. That gives me the VGS. On simplification, VGS becomes VI divided by 1 plus Gm into Rs. So again, the gate source voltage is also reduced by a factor of 1 plus Gm into Rs compared to Vi that is applied here between the gate and the source here. So without Rs, we know that I is equal to Gm times Vi. With Rs, we already know I equals Gm into Vi divided by 1 plus Gm into Rs. Okay, now we will proceed with other derivations here. To derive the expression for output voltage, we know that this two resistance can be made as a single resistance since they are in parallel. So the resistance, total resistance becomes Rd parallel with RL. So now output voltage will be equal to minus I, because its current is going from the ground. So minus I times Rd parallel with RL. So this is the expression for output voltage, minus I into Rd parallel with RL. So we know expression for I here, which is given as which we have obtained as Gm times Vi divided by 1 plus Gm into Rs. If you substitute expression for I, the output voltage now becomes minus Gm into Vi divided by 1 plus Gm into Rs into Rd parallel with RL. Okay. So from this we can obtain the voltage gain expression, which is V naught by Vi. So AV equals V naught by Vi equals minus Gm times Rd parallel with RL divided by 1 plus Gm into Rs. Let us call this as equation 1 here. So with, if you make it RL as infinity, the same AV becomes AV naught. So here RL will get eliminated here. Therefore, the resulting equation is AV naught equals minus Gm times Rd divided by 1 plus Gm into Rs. AV naught is nothing but voltage gain with RL equals infinity. Now to obtain the expression for input resistance, now input resistance is the resistance looking between the terminals gate and source. So from the circuit we can see that it is nothing but the Rg. So therefore Rn equals Ri, which is equal to Rg. Now to obtain the expression for overall voltage gain, let us rewrite the same equation here. AV equals V naught by Vi into, which is equal to minus Gm times Rd parallel with RL divided by 1 plus Gm into Rs. So if we cross multiply this Vi here, so V naught will be equal to minus Vi times the same equation. So now Vi can be obtained. Vi we can see here, if you apply voltage division rule for the circuit here, this Vi in terms of V signal can be written as Vi equals V signal times Rg divided by Rg plus R signal. So that is the expression given here that can be used here in place of Vi, so that we get expression for V naught in terms of V signal. So this is the expression of V naught in terms of V signal, and Gv can be obtained by taking a ratio of V naught by V signal. So V naught by V signal equals Gv, which is equal to minus Rg divided by Rg plus R signal into Gm times Rd parallel with RL divided by 1 plus Gm into Rs. So this is the final expression for Gv, overall or total voltage gain of the common source amplifier with Rs. Now, if you compare all equations, now equation 1, 2 and 3, equation 1 is here, equation 2 is here, which is AV naught equation. First AV equation is equation number 1, AV naught equation is equation 2, and GV equation is equation 3. We can see, you can observe here. So the including Rs results in reduction in the gain by a factor of 1 plus Gm times Rs. That's one of the drawback of common source amplifier with Rs. So to summarize, the Rs in the source leads to the increase in the DC bias stability. That means any variation in drain current such variations will be minimized by having the RS attached to the source terminal of transistor. That's what we have said in the next point here. RS decreases variability in drain current here. This is advantage of using RS in the drain terminal of in source terminal of the MOSFET here. However, RS decreases the gain of the amplifier. So we have a limitation. The RS decreases the gain of the amplifier here. So therefore, RS is also called as source degeneration resistance here. Another interpretation, if you look at equation 1 here, equation 1 is nothing but AB equation. So this is AB equation here. So the interpretation is if you look at numerator and denominator part, so AB is nothing but it is a ratio of total resistance in the drain divided by total resistance in the source. So at the drain point we have a total resistance as RD parallel with RL, and at the source point we have a resistance as RS plus 1 by GM here. So this is another interpretation by looking at voltage gain. So therefore voltage gain is basically depends on the resistance which are passive elements here. Okay, so that is another interpretation of this. So this completes common source amplifier, with a source resistance. To summarize, in today's class we have started with the common source, basic common source amplifier with the biasing scheme, basically a constant current source biasing we have discussed. Following that, we have discussed a common source amplifier with inclusion of source resistance or resistance attached to the source, and we've seen the advantages and drawback of the common source amplifier with RS. So in the next class, we will see the source follower circuit, which has got some different the characteristics compared to the common source amplifier. Thank you all. Thanks for watching this online video.